Hello and welcome to this lecture where we will be talking about the tools and techniques that are used for detection of radio waves from the universe, basically the area of what we call radio astronomy. And I am Yashwant Gupta. I work at the National Center for Radio Astrophysics at Pune, which is part of the TIFR, and we are involved in research in radio astronomy, and I'll talk more about that as we go along. So, I have split today's presentation into 4 parts, as you can see here, starting with the introduction to radio astronomy, telling you how it ties in with the other branches of astronomy and how it started, and moving on from there to talk about some of the basics of radio astronomy, how radio telescopes are built, how they function, how we use them, and moving on from there to illustrate some of these ideas by doing a case study of our own giant meter wave radio telescope, and lastly ending up with talking a little bit about what are the future prospects today for radio astronomy. So, let us start with the first part, which is a very basic introduction, some of which you would definitely be aware of, but we will see how it ties into radio astronomy. So, as we all know, astronomy is the oldest science. It started from the time when mankind turned its gaze up to the heavens and wondered what is up there. And it started obviously with the naked eyes, because that is the natural detector for light waves. And as we see, this is important that you have to have the right kind of detector for different electromagnetic waves. But then when the telescope was invented, there was a dramatic change in the way we could do astronomy. And as we all know, the man who made this happen was Galileo, who turned the telescope to the heavens for the first time in early 1600s, and the rest is history, as we know that we completely changed the way we see and understand the universe. But it is interesting to see how the optical telescopes evolved from the time of Galileo. So, here you can see the evolution of the basic telescopes from the time of Galileo's small telescope all the way to the modern ones, which, as you can see, are very large structures with very specialized instruments. The basic message that I want to convey here is that bigger is better. And the important question to ask is, why is bigger better as far as telescopes is concerned? And there are 2 main reasons. One is that a bigger telescope collects more light, as you can very easily imagine. And when you collect more light, you are more sensitive, and therefore, you can see fainter sources more easily. And this is kind of the reason why when we go into a dark room, our eyes dilate, so that you can open the pupil wider and collect more signal, because you are in a dim light condition. In addition to the better sensitivity that a bigger telescope provides, one very important factor is what we call magnification, which is the bigger telescope allows you higher resolution, which means that you can distinguish between nearby objects or sources in the sky much better, and therefore, you can see more details of objects. So, this is very important, and it is important to realize that both the sensitivity and the resolution of a telescope depend on the size of the aperture. The sensitivity goes as the square of the aperture, because the area is what is important for deciding how much light you are collecting, and the resolution goes inversely as the size of the aperture and the wavelength. So, for a given wavelength, the larger you make the size of the telescope, the better is the resolution. That means it is a smaller value, that means you can resolve objects closer by in the sky. For a given aperture, of course, if you are working at a larger wavelength, then the resolution goes down, and this is what we will see will be of importance when we go to radio astronomy. So, these have been the 2 main factors driving the growth of large telescopes, and we can illustrate this with simple examples. So, this is an example bringing out the ability of the resolution. So, improved resolution. So, you can see the moon here in 4 different views taken with telescopes of different size, from the simplest one where you can just barely make out dark patches on the surface, to this final one here where you can see very clearly details of craters and many other structures on the surface of the moon. So, this clearly illustrates the power of having a better resolution. And you can see a combination of both resolution and sensitivity by taking the case of a well known object, the Andromeda Galaxy, which many of you may have seen even with the naked eye on dark sky, located over here in the constellation of Andromeda. If you look at this with simple Galileo type telescope, you see this simple fuzzy object in the sky, and with the more modern telescopes you see an object like this, where not only can you see much fainter objects, very faint stars and other clouds and objects are clearly visible, but you can also resolve much more detail than you can with a very simple telescope. So, that is just to bring home the point about the importance of the size of the telescope. Now, let us go beyond light waves, which is how astronomy started, and ask this question, that finally light is a form of electromagnetic radiation. As we know, it is part of a much wider spectrum of waves, ranging from the lowest frequency or the largest wavelengths, which are the radio waves, from there to the highest frequency or the smallest wavelength, which are gamma rays. And this picture illustrates that, where you can see the changing frequency over the electromagnetic spectrum going from radio waves to gamma rays, and the kind of sizes that they match to, and the corresponding frequency. And the important question then one can ask, knowing that light is just one small part of this large electromagnetic spectrum, is that can the same object in the universe emit at different wavelengths in the electromagnetic spectrum, and therefore, can it be studied at different wavelengths? And as we will see, the answer is yes. The other interesting question, of course, is that do the different wavelengths give us different information about the object? And there again the answer is yes, and that is very important. And the third one is that other objects or phenomena that can be studied only at some wavelengths, for example, something that may not emit at any wavelength other than optical or any wavelength other than radio. And again the answer is yes, there are objects in the universe which preferentially emit only on a narrow part of the electromagnetic spectrum, and therefore, if you are able to study objects in different parts of the electromagnetic spectrum, then you can get a much more detailed and complete view of the universe. And this is illustrated by this simple picture back to our favorite, the Andromeda Galaxy. And this is the Andromeda Galaxy seen in different wavelengths, going all the way from X-rays to very low frequency radio waves. And what you can see is that the object does not look the same at different wavelengths. There are different parts of the galaxy which become more prominent at different wavelengths, and therefore, it tells us again that you can get complementary information about the object by studying it at different wavelengths of the electromagnetic spectrum. So, that brings us to this topic of multi-wavelength astronomy, that clearly there is a lot to be gained by doing astronomy at multiple wavelengths. The question is, how easy is that to do? And that is where we come up against the couple of hurdles. The first, as we would have noticed when you started with optical astronomy, is that you need the detectors. Our eyes have the natural detectors for detecting optical wavelengths, but you do not have natural detectors for detecting other wavelengths. And so, therefore, this had to wait for technology to develop with time, whereby detectors for different wavelengths could be discovered, built, and then utilized. And so, we all know about photographic plates, which are now used for optical astronomy, charge coupled devices. Radio communication equipment is the one that led to the ability to detect radio waves, and we will come to that in a minute. Second, which is equally important, is that all of these wavelengths from outer space, from celestial objects in the universe, may not reach us at the surface of the earth. And we must remember the ozone layer that protects us from harmful UV rays from the sun. So, when we look at the picture in full detail, we see that there are only two earth based windows. One is of course the optical one, as we all know, and if you look at the other one, it is in the radio band. So, what this shows is the opacity of the Earth's environment, which is a combination of the atmosphere and the ionosphere of the Earth, to the wavelengths over the electromagnetic spectrum. And 100% opacity means that particular wavelength is completely blocked from reaching, and a 0% opacity is the situation where you would get that signal on the surface of the Earth. And so, it is clear that the one major window which can be done with earth based telescopes is this one here, going from a few centimeters or maybe even a bit below, if you can put your telescope at higher altitudes, to a few tens of meters in wavelengths, and that is the radio window. And so, it is then natural that radio astronomy was the next branch of astronomy to take birth after optical astronomy, because that was possible to do with earth based telescopes. So, the question then remained about the detectors, and as I said, the detectors for radio astronomy came as an offshoot from the developments in radio communication technology in 1930s, when man learned how to generate and receive long distance transmission of radio waves for communication purposes. And as often happens in astronomy, the discovery of radio signals from celestial objects was a completely serendipitous discovery, and this is something that we see in astronomy very often. And so, it happened in Bell Labs, where the team was given the job of debugging a transatlantic communication system, which is picking up unwanted noise in the equipment. And this person, Karl Jansky, who was an engineer working in Bell Labs, was given the task of finding out what was malfunctioning in the equipment, or where was the unwanted signal coming from. And so, he built this apparatus, which, believe it or not, was the first radio telescope of the world, though modern radio telescopes look quite different from this. But he built this, and as you can see, it's mounted on a rotating platform which can go around and therefore point in different directions around to see if there is interference signals coming from somewhere. And what Karl Jansky found is that the unwanted signals were not coming from any object on the surface of the earth, but they appear to be coming from a fixed direction in the sky, as can be seen in this very simple plot that he made of the variation of the strength of the signal as the direction in which the telescope was looking. And this soon led to the understanding that there are many interesting objects in the universe which are radiating at radio frequencies, and radio astronomy was born. Initially, it was pioneered by radio engineers, because they are the ones who understood the technique of how to build a radio telescope, a detector, and one of the true pioneers was Grote Reber, who was again an engineer working in Bell Labs, and in his spare time he built this antenna in his backyard, which looks a bit more like what we imagine when we think of a radio antenna. And using this apparatus, he made the first map of the radio sky, which is what you see over here on the top left, where he was able to mark out the brightest sources of radio radiation that his telescope would pick up. And as you can see, they fall in a band which delineates the plane of the Milky Way, and bright objects within the galaxy is the ones that he primarily picked up, including towards the center of the galaxy, Sagittarius, and but there are a few strong extragalactic radio sources also that he was able to pick up. And so, from there we have moved on a long way in the growth of radio astronomy. So, what we will look now in part 2 is some basic ideas of how a radio telescope works, how it functions, what are the important concepts, and what are the various technologies that are used in building a radio astronomy observatory. So, in a very basic sense, a radio telescope is no different from your favorite satellite dish with which you receive your TV channels, but there is a important difference, which is the fact that unlike the man-made signals which the satellite is sending down to your satellite receiver dish, the celestial signals that we are trying to detect are very weak. And in addition to that, there is corruption of the signal due to noise that is picked up by the electronics of the receiver system as well as from the environment. But just to understand how weak the signals are, radio astronomers use this unit called the Jansky in honor of Carl Jansky, which is 10 to the minus 26 watts per square meter per hertz of incident intensity of the wave. And as you can see, that is a very small amount of power, and if you were to try and understand that in different ways, you could do it. If you understand a bit of electrical engineering, then if you were to use a typical telescope with say of the order of 1,000 square meter collecting area and a reasonable bandwidth and ask how much power you are getting, it is a very small power, it is minus 100 dBm, where 0 dBm represents 1 milliwatt of power. So, you can see it is a very weak signal. Equivalently, if you are more physics inclined, then if you were to calculate the total energy that a typical radio telescope would collect in 1,000 years of continuous operation, it is 1 millijoule, and that again is a very tiny amount of energy. So, that is just to drive home the point that the signals are very, very weak, and when that happens, you have to take a lot of care in picking up the signal from the antenna and processing it, amplifying it to the level where it can be conveniently detected or recorded. The second thing that you have to be careful is that any corrupting signal, whether coming from within the electronics, as we all know that every piece of electronics generates some intrinsic noise, and if that noise overwhelms the strength of the signal that we are receiving, then it becomes very difficult to detect that signal. In addition to intrinsic noise, you can get corruption from ambient signals, man-made signals, man-made interference. So, one has to be very careful when designing a radio telescope, so as to minimize the noise, and there are ways in which the intrinsic noise can be minimized by building the electronics with special devices which minimize the noise, including cooling of the most critical parts of the receiver system to low temperatures to reduce the noise from the electronics. So, finally, what happens in order to get the high sensitivity, so that you can see faint sources out to distant reaches in the universe, one needs to build large dishes, so that you can get as large as square meter of collecting area, and one needs to build high quality low noise electronics to minimize the corruption due to noise. The other thing that helps, of course, is that as you can see, this is per hertz, and so if you have a naturally emitting radio source which is emitting over a very large bandwidth, then if you can receive the signal over that large bandwidth in the radio receiver, then again you can increase the amount of power that you are getting from the source. So, of course, this works for sources whose natural bandwidth of emission is quite large. It will not work for sources which emit spectral lines, for example. Finally, you can improve the final signal to noise of your detection by integrating the received signal over a long duration of time, and that is because any noise that comes along with the signal only grows as the square root of the time of integration, whereas the strength of the signal increases linearly with the time of integration. So, you can improve the signal to noise by observing the source for long durations, and this is often done in radio astronomy. And we will see that it is also done for another reason when we come to the next issue, which is about the resolution. But before we go to resolution, we can have a quick look at the different types of radio antennas that are used, and to some extent the kind of antenna that you use varies depending on the frequency or the wavelength at which one is working. So, for example, at very long wavelengths, longer than a meter or so, one prefers to use wire antennas such as dipoles and Yagis, the kind that are shown on the right here. And as you go to shorter wavelengths, less than a meter, then the dish antenna, which is the more traditional kind of radio telescope, is the preferred model or preferred design. And in between there are hybrid antennas where one uses wire reflectors and reflectors with dipole feeds, which work well when you have intermediate wavelengths, which are say of the order of a meter or so, which is around a few hundred megahertz of frequency. So, when characterizing an antenna, there are a few basic features or parameters which one needs to understand and therefore control in order to get an antenna with optimal performance. And this is illustrated in this figure here, where you can see that the basic thing is of course the primary reflector with either a subreflector which brings the signal to a focus down below here, or you can have a primary feed where you pick up the signal right at the primary focus, and again we will see examples of that in a minute. The antenna of course then needs to be on a mount which can rotate in two primary axes usually, the azimuth axis which allows you to move the antenna in the azimuth direction, and the elevation axis which allows you to move the antenna in elevation up and down, so that you can point at different directions in the sky, and of course the ability to track the source as the earth rotates. Now, when you do this, effectively the antenna has the property that it is characterized by what we call a primary or a main beam, which basically represents the angular pattern of the response of the antenna, much like the airy pattern that one is familiar in optical astronomy, which basically tells you that as a function of angle around the direction in which the antenna is pointing, what is the response of the antenna to wave fronts coming from the particular directions. And normally the antenna will have a main beam, and this main beam is directly related to the resolution. So, the angle of this main beam goes exactly as the lambda by d, the resolution, and you can see the connection that the wider the main beam, the poorer will be the ability of the antenna to resolve two objects which lie within the main beam in angular separation. And therefore, in order to have an antenna with better resolution, you want to reduce the size of the main beam, which means either you have a larger aperture or you have a smaller wavelength. But in addition to that, the antenna can have low level of response in angles which are very far away or relatively far away from the main direction in which the antenna is pointed, and these are called side lobes, and one again has to worry about them, because if you are trying to observe source in a given direction, you do not want the antenna to be confused by picking up signals from a source which is at some relatively far away angular position in the sky, but whose signal is picked up by the much weaker side lobe response of the antenna. So, the design often tries to minimize the amplitude of these side lobes, so that most of the signal is picked up by the antenna from the main lobe. So, all of this goes into the sophistication of the design of the electromagnetics of the antenna system, which we will not have time to go into the details, but certainly we can appreciate the fact that the reflector types and the feed arrangement can be of different configurations. ranging from the very basic simple prime focus one, where you put the element that converts the electromagnetic field of the incoming radiation into a electrical voltage or electrical current, which we call a feed element, right here at the focus, which is relatively easy to do, but it has its pros and cons. Alternatively, you can put a secondary reflector at the focus in a Cassegrain arrangement, whereby you pick up the final signal down below. It can even be below the main reflector. And then there are various variants such as an offset Cassegrain, an azimuth, and more complicated beam waveguide structures, and what is called an offset parabola, where the parabolic section is such that you cut it off from the full parabola and take only one half and use that and bring the signal to a focus in a Cassegrain fashion. And you can ask, what is the advantage of doing something like this compared to the Cassegrain or the prime focus, and that is what is called blockage. So, if you have something which is above the reflector, then it blocks some of the incoming radiation, the plane wave coming in, and you lose a little bit of the sensitivity, and you also get some amount of corruption of the beam shape or distortion of the beam shape, because there is a non-uniform illumination by the incoming electromagnetic wavefront. Whereas, in an offset situation, you avoid that and you have an uninterrupted unblocked aperture, and but then this is obviously a harder mechanical arrangement to build and support, because it is inherently asymmetric in its arrangement, and the mechanical support structure tends to be more cumbersome. And here are actual real examples of antennas which follow these different ideas. So, our own GMRT antenna is a prime focus, and then the other examples of telescopes around the world with the different arrangements, and here is an example of the offset parabola. And all of these are built and used, and as I said, they have their pros and cons depending on what is the prime goal and how expensive you can afford to make your telescope. And the question of complexity and expense also comes in when we talk about the surface of the reflector and how accurate it needs to be. And that again depends on the wavelength of the operation. And as you all would know, if you have a reflector, then it acts as an ideal reflector for a wavelength lambda if the surface is accurate to some fraction of lambda, and as a thumb rule it is lambda by 10, it can be say lambda by 20. And so, if you have a wavelength which is long enough, then you can actually make the reflecting surface from a mesh rather than from a solid, as is shown in the left side with the GMRT antenna, where it appears to be a transparent reflecting surface, but actually it is not transparent. There is a fine mesh here, as compared to the antenna on the right, which is a high frequency antenna, which is completely solid metal panels which make up the parabolic reflecting surface. And obviously, there are differences. The antenna with a mesh will be much lighter for the same size as compared to an antenna with a solid surface, and therefore easier to build, and with a much lighter support structure, because the wind resistance that is felt by a porous antenna with a mesh is much less than the wind resistance that you would feel when you have a solid panel facing the wind. And therefore, when you have a higher force of the wind due to the solid panel, you need a much heavier backup structure to support the antenna and keep it stable, and that increases the weight of the antenna. And then finally, you have to move this antenna to drive it, and the heavier the antenna, the more expensive and complicated is the drive train that is required in order to move the antenna, position it, and track sources accurately in the sky. So, as a result, we often find low frequency antennas have a different design philosophy and a different configuration and the way they are built as compared to high frequency antennas. And it it makes a difference finally when one has to understand the larger effects, the bigger engineering problems and the cost to benefit ratio when you build such antennas. And as I said earlier, that you need to mount this antenna to track sources, and as we all know, there are two popular kinds of mounts. The equatorial mounting arrangement, where you have one fixed axis and one rotating axis, where the polar axis needs to be aligned with the Earth's rotation axis, which means this angle has to be equal to the latitude of the place, and the altizimuth mount, which is easier to build, but has two axes and therefore more complicated to operate. Now, we move on from there to the other major point that we noted when we talked about the need for large radio telescopes, which is the question of resolution. As we discussed earlier, that both the sensitivity and the resolution depend on the size of the aperture, and you can build a large aperture, then you will get higher sensitivity and a better resolution. But then, as you can imagine, there would be practical limits to how large a radio antenna you can build and still have it fully steerable. And some of the largest antennas that we have today, which are fully steerable, are of the order of 100 meters in diameter. An example shown here on the right is the 100-meter Green Bank radio telescope in the US. 100 meters, as you can imagine, is quite large. But if you ask what is the resolution that a 100-meter size radio telescope would provide, then it's only half a degree at a 1 meter wavelength, that is a 300 megahertz frequency. And half a degree is very poor resolution compared to what even the simplest optical telescope would achieve, simply because the wavelength at optical is much smaller than the wavelength at radio. And that is illustrated by the examples shown below here, where we go back to the moon, and the resolution on the moon, as we saw even with the simple optical telescope, you can start seeing details of the various features on the moon. But if you were to use a 100-meter size radio telescope to look at the moon, it would appear just like this blurred circular disk without any ability to be able to resolve the features, but that's about half a degree, 30 arc minutes. And so that drives home the point that the major disadvantage that radio astronomy faces when it comes to resolution. And if you look at a galaxy, you will see a similar picture. You would see image detailed features of Andromeda, but if you were to look at it with this single dish of 100-meter size, you may get an image which looks like this one, where you can just barely make out any detail. So people do try to build larger single dishes, but they are the ones which are fixed in the ground and cannot be moved, and therefore cannot easily track over a large region of the sky. So this is an example of the 300-meter Arecibo radio telescope, which has been around for several decades now, and there's now one in China which is 500 meters in size, but they are fixed in the ground, and only the feed element here at the focus has some ability to be moved so that you can get some limited coverage in the sky. So they act like transit instruments, but with some limited ability to look around in a range of angles around the zenith that the antenna is pointing to. So that's not very good, and this major disadvantage of radio astronomy took a while before it was discovered that you can actually synthesize a telescope of large size as far as resolution is concerned by spreading out many smaller individual antennas over a large area. So as an example, I have shown here an array antenna called the Very Large Array Telescope located in the US, where you can see lots of relatively small antennas. They are still of the order of few tens of meters in size, but many of them, and spread out over distances which are of the order of tens of kilometers in extent. And this idea that you can actually combine the signals from these antennas in a manner whereby you can recover an image with a resolution which is effectively what you would have got if you had built a single dish whose diameter was equal to the area over which the individual antennas are spread out. And this technique is called aperture synthesis, because you are basically synthesizing a larger aperture by using many smaller apertures. And the word earth rotation comes in front of it, because I will explain in a moment how aperture synthesis works, and then we will appreciate what role the earth rotation plays in it. But as I said, this allows you to replace lambda by d by lambda by ds, where ds is the largest separation between the antennas. So, this basically allows radio astronomy to overcome this major challenge of poor resolution without having to build these very large single dishes, which are impractical beyond a certain size. By building smaller antennas, spreading them out over a larger distance, and then combining the signals from them in appropriate manner, which brings its own challenges. And to do that, we need to understand how the technique works. And effectively, for those of you who are familiar with the Young's double slit, each pair of antennas effectively acts like a double slit. What that means is that when you combine the signals from a pair of antennas by correlating them in what is called a correlator to get the cross spectrum, you are effectively picking up one sinusoidal oscillation on the sky plane. Effectively, you are measuring one Fourier component of the spatial distribution of intensity on the sky, and it is a two-dimensional spatial intensity distribution. Any image in the sky can be considered as a two-dimensional image, and if you were to decompose the two-dimensional image into a two-dimensional Fourier transform with its Fourier components, then you can show mathematically that a pair of antennas, when the signal from those is combined in this manner, is actually responding to or picking up the Fourier component, whose Fourier frequency depends on the wavelength and the vector separation between the antennas. And now you can see that if you had many of these antennas, then if you were to combine the signals from the antennas pairwise, then you would be able to synthesize the different Fourier components of the image in the Fourier plane. And if you have enough of them, then you can actually solve the problem of taking the inverse two-dimensional Fourier transform of that data to reconstruct the two-dimensional intensity distribution in the sky. And this is the basis of the technique called aperture synthesis. The important point here is to note that it is the vector separation between the antenna as seen by the source that is important. And as you can imagine, if you had two antennas which were east-west in their orientation, then as the earth rotates, the effective projected baseline that the source sees for an east-west antenna changes as the source rises to the time it transits to the time it sets. So, the baseline appears foreshortened when the source is rising and when the source sets, and when the source is vertically above, it sees the full east-west baseline. So, effectively from the same pair of antennas, as a function of time from the time the source rises to the time the source sets, you can actually measure different Fourier components of the image, and that is why the earth rotation is an important part of the aperture synthesis technique, and that is why you often end up observing the source over a long track from the time it rises to the time it sets using this array of antennas, so that you can reconstruct as many Fourier components as is possible. Of course, as you can see here, there is a fairly complicated signal processing that needs to be carried out in order to do this calculation, and some of this has to be done in real time in order to be able to keep up with the rate at which the data is coming. And once you integrate the data after correlating it for some time, then you can actually record it and do the rest of the processing offline to make the final two-dimensional inverse Fourier transform and the image. So, this just gives you a basic idea of how this is done, and then let us look at some examples of what it achieves. So, this is an example of a radio image of a particular object called the Cygnus A, which is a radio galaxy made with the best image made before the VLA instrument, which I showed a short while ago, was built. And you can see that there is a object here with the radiation from the center and radiation from these two lobes of the radio galaxy. But this is an image of the same object made with this VLA array, and this is of course different in the sense that this is a false color grayscale image compared to the top one, which is a contour image. But nevertheless, the point is very clear that you can see much better detail in the lower image. That means this has a much higher resolution. You can make out that the object at the center is a very small compact object. You can make out a jet of radio emission from the central core of the object to the lobes of the radio galaxy, and you can see much more detailed structure in the lobes of the radio galaxy. So, this just illustrates the view that these large aperture instruments provide in radio astronomy. You can of course ask that how far can you extend this concept of array telescopes? Can you do this beyond few tens of kilometers, which is what I was showing? And yes, in principle, as you can imagine, you should be able to do it with antennas which are spread out over an entire continent, and then you would get extremely high resolution of the order of milliarc seconds, which would even start doing better than some of the optical telescopes, where you are often limited to an arc second of seeing in ground based optical telescopes. You would of course ask that how would you get the data together and do the signal processing, and that is what would be a technological challenge in this, which is initially in the early days it was overcome by being able to record the raw voltages at high speeds on local recording machines, specially designed recording systems, and then transporting those tapes as they were in the early days to a common place where the data was read and the signal processing relating to the correlation was carried out. And you can then even extend this to intercontinental long baseline interferometry, where you do this with antennas spread out between continents, and again that is practical. It is possible to do that, and today the fact that you have optical fibers connecting pretty much every place on the earth allow you to carry these signals in quasi real time from the antennas to the central processing place, where you can carry out the processing and make the images. You can of course extend this to one level higher and ask, can I do this with antennas on the earth and antennas in space? And yes, this is again, as you can imagine, is conceptually possible. It is a thought experiment that you could easily think of, but to convert it into reality is a bit more challenging, but it has been done. So, you can actually send antennas, radio antennas on space probes and reach to a certain location above the earth, unfurl them, make a proper reflecting surface, and then be able to observe the same source with this antenna as with ground based antennas, record the data at the places, and then transmit the data from the space based antenna to the ground with the regular space communication equipment, and then correlate the data between the ground based antennas, space based antennas, to get now effective baselines which are several tens of thousands of kilometers, and therefore very high resolution. This is an example of the kind of study where the very central region of a quasar can be resolved in radio wavelengths to show that there is very fine structure at milliarc seconds and finer scales that can be detected. And so, this has been used now quite effectively for very specialized kinds of studies in radio astronomy, and it tells you as to how far you can go today with this technique. So, with that we will move on to the case study of an overall radio telescope or observatory, and we will take our own GMRT as an example. So, the Giant Meter Wave Radio Telescope is a world class radio facility which is built by NCR-ATIFR and built during the 1990s and operational since 2002. It is specialized for low frequency applications, typically in the range from 50 to 1450 megahertz, which is towards the lower part of that large radio window that I showed earlier. And it is an array telescope, consists of 30 antennas. Each of them is fairly large in its own right, 45 meters in diameter, and it is one of the largest facilities at these frequencies in the world today. And a bit like the VLA array that I showed you, the antennas are roughly in a Y-shaped structure on the large scale, with a set of antennas in a compact configuration in the center, which we call the central square, 1 kilometer by 1 kilometer region with 12 antennas, and the remaining 18 spread out in a Y-shaped arrangement going out to largest distance from the center, which is a bit over 14 kilometers, and thereby allowing you to synthesize an antenna as far as resolution is concerned, whose area is equivalent to that of a 28 kilometer size dish. And this works quite well, and here are some pictures. Here is a Google view of the central square, 1 kilometer by 1 kilometer region, showing you these specs, which are the individual antennas. Here is a zoomed in view where you can start making out the individual antennas. These are the 3 of the closest antennas which provide the shortest baselines in the Fourier synthesis, and this is the central building where the signals from all the antennas are brought over optical fiber, and then the signal processing that I described earlier is carried out in digital processing systems over here, and the control room from whereby the entire array is controlled is located right here. This is a view from the nearby hills showing the central square antennas. This is a close up of a single antenna, as I said, 45 meters in diameter, a pretty large structure, and it is a prime focus instrument. So, you can see the main feed elements which pick up the radio waves, convert them to electrical signals located at the focus, and this is the kind of crane that is needed in order to be able to access and work at the focus of the antenna in order to either replace electronics, put new things, maintenance, and so on. And so, as you can see, it is a fairly challenging task, and you can imagine building such a large structure is equally challenging. This shows a sequence of how a single antenna was built. The tower on which it sits is a 3-story high tower, and then the structure is assembled on top of it. The antenna itself is built on the ground and then lifted up, hoisted up on these 4 cranes to the top, and then bolted in place to get the final working system. As you can see, it is a mechanical challenge. Not just mechanical, there are many subsystems that make up such an instrument, which all are technologies that one needs to master in order to have a good quality observatory, ranging from the mechanical subsystems, the servo systems which are important for accurate positioning and movement of the antenna on the 2 axes, then the electromagnetics, the antenna feeds which you put at the focus. Here you can put feeds of 4 different kinds at the focus, and there is a rotating turret here at the focus which can rotate and bring the desired feed to the focus that is pointing to the dish, so that it can pick up the reflected signals. And then the signal, the voltage signal that you pick up is, as I said, very faint. It has to be properly conditioned, amplified, brought down to the bottom. So, there is electronics right at the top, which is the most crucial electronics, which does the initial amplification and conditioning of the signal, is brought down over cables to the bottom of the dish, where there is further conditioning, and then it is transmitted over optical fiber. So, there is a lot of optical fiber technology in order to send it to the central receiver, and then it is digitized there, and then the rest of the signal processing is carried out. And in order to control all of this, there is a very sophisticated monitor control and telemetry system, because everything is controlled from the central facility in an automatic fashion, whereby you can run an entire chain of observations for several hours, if not many days, from the central control room. And so, there is fairly sophisticated software for doing all of that, and finally, software for the offline processing, which allows you to take these Fourier components and do the imaging process to make the final radio image of the sky, which again has fairly sophisticated issues that one needs to understand and overcome, including how do you calibrate the data and so on. So, this is just a very simple block diagram flow chart of the receiver system, starting from the feed element at the antenna focus to the front end electronics at the focus, to the antenna base receiver system, the fiber optical transmitter and the transmission on optical fiber, to the central station, where it is received, and an analog processing chain and a digital processing chain, all with their proper control for setting the frequencies and selecting the frequencies correctly, and so on. So, the original GMRT system had a bandwidth of 32 megahertz. If you remember in the when we talked earlier, that the larger the bandwidth that you can build for your receiver system, the more signal you can collect, and therefore, the higher the sensitivity for observing sources which emit over a large range of frequencies. And so, the original GMRT was designed for 32 megahertz of bandwidth, which is reasonable, but by today's standard fairly modest, and we'll see that in a minute. And it can also process signals for observing pulsars, which are compact radio sources, which require a slightly different signal processing than is needed for making the images of larger objects such as nebulae and galaxies. Okay, so the GMRT, as I said, was built in the 1990s, and it was dedicated as an international facility from late 2001 onwards, and 2002 onwards regular observations started with the GMRT, and people from all over the world use the facility, as you can see here, with a healthy participation. About 50% of the proposals from India, and others from astronomers from literally all over the world. It is a highly oversubscribed instrument, in the sense that the demand is always a factor of 2 to 3 higher than the amount of time that we have available for scheduling observations, and which means that the process for getting time on the telescope is fairly competitive in terms of the best proposals with the best ideas that get time. And a typical radio facility like the GMRT is used for a very broad range of science topics, which are listed here, all the way from studying the details of the radio emission from the sun and its properties, to even looking for extrasolar planets, and then studying objects like pulsars and galactic objects like supernova remnants, microquasars, explosive transients like gamma ray bursts, then different forms of hydrogen gas, ionized or neutral, both in our galaxy and in other galaxies, and radio properties of different kinds of galaxies, studying clusters of galaxies, and what are called radio galaxies, which are galaxies which emit preferentially strongly in radio frequencies, like the example that I showed you when I was illustrating the power of the resolution. That is a typical radio galaxy, and further beyond that, cosmology, the epoch of reionization, and other topics. The other kind of studies that a large facility like the GMRT is often used for are what are called all sky surveys. So, you can carry out a uniform survey of the entire sky visible from the observatory, and make images of the entire sky. It is like an atlas of the universe, but at a particular frequency. In this case, the GMRT has been used to make a very sensitive all sky survey called the TGSS at 150 megahertz, which was not available for astronomers before that at that frequency with that kind of resolution and sensitivity, and that gives you again a very complementary view of compared to a similar atlas made at a higher frequency, and you can then look for sources which are common, which are not common. You can study the same source over a wide range of frequencies. You can do various kinds of statistical studies about the distribution of sources in the sky, and lots of new ideas can come by studying the objects or results produced from such surveys. And many new results have been published using the GMRT. And what we have done now recently is to complete a major upgrade of the GMRT to improve its sensitivity by more than a factor of 2, and also make it a much more versatile instrument, which will keep it on the forefront in the global scenario for the next decade or so. And so, the main feature in the upgraded GMRT is to provide nearly seamless frequency coverage from 120 to 1450 megahertz, which we are likely to extend down to 50 megahertz, and improve the instantaneous bandwidth to 400 megahertz from 32 megahertz, and also have improved quality of the receivers with higher sensitivity and better rejection of the unwanted man-made radio noise that is often present. And this is an example showing the improvement in the frequency coverage. So, the small white boxes show the frequency coverage that the old GMRT system offered in this range of frequencies from about 100 megahertz to about almost 1500 megahertz, and the purple boxes show the improved frequency coverage which is now available, and the y axis shows what is called the fractional bandwidth. That means, there is one observing band from this frequency to this one, which has a large fractional bandwidth compared to the center frequency, and the fractional bandwidth of course decreases as you go to the higher frequencies, where the bandwidth, though it goes up, is still the maximum is around 400 to 450 megahertz. And the gaps here, which you would wonder why some gaps have been left, these are places where there is very strong man-made transmissions, which are so strong that it is impossible to operate the radio antennas in those regions. The signal is completely corrupted. So, these are TV transmissions, mobile phone transmissions, which we avoid, but try to cover the rest of the frequency space which is available. And this is an example of the improvement in the performance that the upgraded GMRT offers compared to the legacy system, where the legacy system sensitivity for what is the best quality image that you can get from a 9-hour long aperture synthesis observation of a typical source improves. That means, you can get better sensitivity, lower value in Janskis. It is in micro Janskis here that you can measure, and going from the blue filled circles to the purple filled circles is the improvement in going from the legacy GMRT system to the upgraded system. And what it also shows is the sensitivities that the other facilities in the world either currently operating or expected to come online in the near future. And you can see that compared to most of the other facilities, the upgraded GMRT is expected to perform quite favorably until you come to these symbols with the stars, which is the square kilometer array, which we will talk about in a short while, which is still a project which is still in the design and planning phases. But the basic improvement that the upgraded GMRT provides is by a factor of 3, mostly a combination of the larger bandwidth and the better quality receivers with lower noise. Okay, so that brings us to the last part, which is to look ahead to the future and ask the question that what lies ahead in the realm of radio astronomy. And as we saw, whether it is the upgraded GMRT or even plans that we have for further enhancing and expanding the GMRT, there are other plans and other facilities that are coming up. The LOFAR is a low frequency array in Europe, which is actually now under operation and is producing results. ALMA is International Millimeter Wave Radio Telescope, which is again also now producing results in Chile. And there is now the thing that the radio astronomy community is really looking forward to is a square kilometer array, which is currently in the design phase. And so, we will talk a little bit about what is the SKA and what does it promise. So, this is the most ambitious radio astronomy project ever attempted, and to understand that is a plot here which shows as a function of time, that is over the years since the time Grote Reber, whom we talked about earlier, built his first radio telescope back in the 1940s, to how the sensitivity of radio telescopes has improved over the years. And somewhere here you see the GMRT at the time when it was conceptualized and then built, and the upgraded GMRT would fall again on this line somewhere over here. But what the SK aims to do is more than a factor of 10 better than any of these existing facilities, and that is something that is expected to be 30 to 50 times better than the world's best radio telescope, with a total collecting area of 1 square kilometer, which is the where gives the name the square kilometer array, which is 30 times the collecting area of the GMRT. But it will have many more antennas than just 30 times the 30 antennas of GMRT, because the antennas for the SKA will be smaller in size than the 45-meter diameter dishes of GMRT, so that they can see a larger field of view at a given time. And it will have a much higher resolution, because it will have antennas spread out in the final configuration up to thousands of kilometers, but connected in real time by optical fiber, and a much wider range of frequency coverage from tens of megahertz to 10 gigahertz or so, and located in very radio quiet regions of the world, semi-desert regions in Australia and South Africa, far away from man-made sources of noise, and will have cutting edge science applications. So, it will sit right up there along with all the next generation mega facilities, the optical facilities such as the TMT and the GMT, the ALMA that we already talked about, and the next generation optical space telescopes, the James Webb, and the gravitational wave detectors like the LIGO. And it's important and heartening to note that out of these, India is participating in at least 3 of these large international projects that are shown here, the optical, the LIGO, and the radio. And so, as you can imagine, a telescope of the kind of specifications that the SKA is designed for requires cutting edge technologies in various areas, whether it is the design of the receptors themselves, there is the design of the electronics, the optical fiber signal transport system, where the total network traffic will be larger than the total global internet traffic that we see today, and state of the art signal processing and supercomputing requirements for being able to analyze the data and make images, and a very complicated management structure to manage these far flung spread out antennas operating from 2 different continents. And so, there is a lot of technology development that is required in order to make the SKA happen. And since SKA itself is very challenging, it is split into 2 phases. Phase 1 is just 10% of the final specification of the SKA, which is still a fairly sophisticated instrument, can be used for many cutting edge science applications. And it is to be built with a slightly limited frequency range and a smaller extent in area as compared to the final array, but built to keep all the infrastructure and design ideas so that it can be expanded to the full SKA later on. And the 2 sites that I mentioned with the global headquarters in the UK. So, truly a multinational project with 10 different countries that are taking part in this. And as I said, currently in the design phase, which should complete by the end of 2019 and to be built from 2020 to 2025 at a fairly large cost as shown here, with different countries contributing to it. And here is a pictorial representation of what the array would look like in South Africa, which would be the mid frequency array using these dishes, but these are the offset paraboloid dishes that we talked about in the beginning, different from the prime focus dishes that the GMRT uses. And that is a completely unblocked aperture and located in a semi-desert region in the northern part of South Africa and extending from there outwards to larger distances. And the low frequency part of the SKA working from around 50 to 350 megahertz, a very different design using dipoles, which is what I mentioned in the earlier part, that at very low frequencies one tends to move away from dishes and uses fields of dipoles, where a field of many thousand dipoles like this would effectively act like a single antenna or a station is what it is called. Again, a lot of sophisticated signal processing to combine the signals from each of these dipoles in order to make it look like a single station, and then many such stations, just like you would have many antennas spread out over a large region. And again, located in a semi-desert region in Western Australia, far away from the nearest cities. And the partnership, which is a global partnership with many different countries working together right now, more who are interested and may join in the near future, and work which is coordinated from the central project office located in the UK. And when you talk about the kind of science that is possible with the SKA, it is truly transformational, and I have listed here the different topics which range all the way from the very early universe, the cosmic dawn, the epoch of reionization, to cosmology, dark energy, evolution of galaxies from their study of the radio continuum emission and the neutral hydrogen emission, the origin and evolution of cosmic magnetism, transient radio sources, fast radio bursts and various such phenomena. Very interesting tests of strong field test of gravity using pulsars and black holes, which are envisaged to be feasible with the square kilometer array. Even topics which border on astrobiology, detecting protoplanetary disks, searching for complex molecules which can be the building blocks of life, to even searching for extraterrestrial intelligence, what we call SETI, which is one of the very interesting areas that radio astronomy pursues. Haven't had a successful detection yet, but that would happen any time. That would be a great discovery. And finally, when you build any facility which is 10 times better than anything else that exists, astronomy always throws up the unexpected discoveries, what is called serendipitous science, because there's always new things out there in the universe which we don't know about, and the moment you have better abilities to see the universe, you start seeing the new features. So, with that look at the future of radio astronomy, I'll end with a very quick and very brief summary that radio astronomy is the study of the universe through the fairly wide radio window in the electromagnetic spectrum. It's one of the two windows that is accessible with ground based telescopes, and therefore much easier to do than the other windows where you have to build telescopes which have to be flown on space missions to get above the limitations of the Earth's environment. And therefore, radio telescopes can be large dishes, but as we saw that there are limitations even to the largest radio antennas that you can build, and the radio astronomy has moved to the concept of having arrays of antennas spread out over large distances in order to achieve the sufficiently high resolution that you aim for. And as we saw, this can go not just to baselines or antenna distances which are of the order of what could fit in a country, but what could fit in a continent, and even between Earth and space-based antennas to get some of the highest resolutions. And as we saw very briefly, that many kinds of sophisticated engineering and technology are needed for building a modern radio astronomy observatory and making it fully functional to get the best out of it. And an example that we looked at was our own giant meter wave radio telescope, which is a facility that runs in India and has produced many interesting results in the last several years, and is being upgraded to improve its sensitivity and to make it a more versatile facility and keep it in the forefront of global radio astronomy for the next several years to come. In the longer term, we looked at what may be the future of radio astronomy, which is large multinational projects like the Square Kilometer Array, where all nations coming together to build a truly large scale facility at the best possible sites on the surface of the Earth. And the SKA promises revolutionary science, but requires next generation cutting edge technology in order to implement it. And the design work for that is currently ongoing, expected to be finished by next year to 2019, and construction expected to start from 2020, and facility available for use from around 2024 or so. And that truly would be a revolutionary facility which astronomers from all over the world are very much looking forward to. So, with that we come to the end of this lecture, and I hope that has helped you to get a good basic understanding of radio astronomy and the facilities that we use and how we build them, and what kind of technology goes into them, and what kind of results and capabilities are possible with them. Thank you.